Thank you very much, Tino, for organizing this event and for me being here today with you. I have been working with CRISPR technology for over a year now, and today I'm going to give you a short introduction of what is this technology about. First, has anyone ever heard about CRISPR? Oh, wow, I'm very surprised. Good or bad, we are going to discuss it later. So I would like first that we can watch an introductory video made from the Food Information Council, and then we can talk a little bit in detail of why this technology is important, how we can practically intervene into the genome of yeast, and what are the future perspectives with the applications of CRISPR-Cas9. All right, let's talk a little bit more in detail of how the CRISPR-Cas technology, this novel genome editing tool, works. As you can see in this image, in the middle of the image, this is the double-stranded helix of DNA. And the gray shape around is the Cas9 enzyme, which is an enzyme that will work as scissors. It is going to target the gene of interest that the scientists have selected, and it's going to create a double-stranded cleavage. How this can happen? We utilize a guide RNA designed complementary of the part of the gene, and this RNA will work as a molecular GPS. Will guide the enzyme into the site-specific point. You can see here in the arrows, this is the exact site where the cleavage will be introduced. And the site specificity is also achieved by an introduction of a pump site, a 3 nucleotides pump site, directly upstream of the guide RNA. And the advantages of this system over already pre-existing models of genome editing is that it's cheaper, quicker, and more accessible to researchers. And this technology has been demonstrated to work successfully in all common modern organisms. So as I said at the beginning, I have been working with this technology, and I have edited brewing yeast strains in order that we can achieve better beer and in a more sustainable way. And so how practically a scientist can intervene the genome of yeast? We insert into the yeast 2 plasmid vectors. Plasmids are circular DNA molecules, which we can design and create with all the necessary information needed for the Cas9 system, meaning that those plasmids, they will reproduce independently in the genome of yeast, and will carry the Cas9 enzyme, the expression of this enzyme, the guide RNA, and when the cleavage will be introduced, we need to repair it. And then we insert the change, the desired change that the scientists have decided with a repair template together, all of them designed in plasmids. And I'm sorry for my poor drawing. I think I'm better doing lab work than sketching. And as I said, the yeast, in yeast genome, there are many genes of interest. And yeast is not only responsible for alcoholic fermentation, it also gives many flavor molecules, aroma and flavor molecules in the final product. But not all of them are good. In my project, I decided to reduce a molecule produced during beer fermentation that is creating a butter of flavor which is unwanted in the final product. And it's, in general, a major disadvantage to have this compound in brewing industries. So selecting the gene of interest, the gene that is, will be expressed as diacetyl, and then using the CRISPR-Cas system, knocking out the gene with deletion of 2 base pairs will end up in a dysfunctional protein and then a reduction in the production of diacetyl. And it's also important to test that the strains work, that the strains can create beer. And if the change is integrated in the genome, then there should be no production of diacetyl anymore. In this moment, I would like to thank Preben Hansen from DTU Brewery for his help in creating yogurt every time for my beer fermentations, and also Professor Mikkel Pedersen from the Copenhagen University, the food department, for his help in analytics and determination of the diacetyl compound. So what are exactly the results of this study? It worked. So CRISPR was actually worked and edited the genome, so we had 60% reduction of the production of diacetyl in the final product of in beer products produced with those novel strains. And what does it mean practically? So the maturation period that it continues the beer fermentation in breweries was decreased from 4 weeks to 2 weeks. And this prolonging the maturation period and the conditioning period is the only way that microbreweries have today to reduce the unwanted diacetyl in their final products. Staying in the brewing industry and applications in CRISPR applications in the food industry, I would like to illustrate another example. In this study, we are not deleting genes, we are integrating new genes from another organism into yeast. You all know that in yogurt production and in beer production in general, we utilize hops. But hops is a very demanding plant to cultivate. It's very water demanding, and also it is in danger due to global warming. So scientists integrated aroma and flavor compounds originally from hops into the yeast genome, meaning that final products from those engineered strains resulted in the same taste and the same flavor profile as beer products without the addition of hops. Another food application, CRISPR food application, and you may also have heard it, it's the CRISPR cabbage story. Professor Stefan Jansson from Umeå University in Sweden created a cabbage in which he deleted a gene that is affecting the growth of the plant. And Professor Jansson was passionate about his plant, that he had no difference between the original plant and this mutated new cabbage. So he cultivated, cooked, and ate a pasta with pieces of the cabbage that he created. And Professor is still alive and doing great research, meaning that it's actually true that the plant that he made, they had no difference from the original crop that he used. But not only CRISPR applications are positive. And in this picture, we can see Aaron Trewick, a biohacker and leader of a biotech company, and in which he was invited in a conference in Texas. In this conference, he injected himself into a herpes therapy, which he created together with another biohacker. And the difference with his therapy is that there were no clinical trials and no FDA approval for utilization, for actually therapeutics of this, of his treatment, of his proposed treatment. And it is important, and it's actually quite disturbing, this example, because scientists and scientific projects should always be according to the FDA approval and the regulations. That's the point, that's what we need to discuss today. We cannot just find a new technology and begin to do whatever we would like without following the regulations. And another more controversial and even more disturbing experiment about with the CRISPR application, the CRISPR baby experiment. Maybe also you have heard this. It was out in the news like last month. And a team of scientists in China, I'm afraid I don't remember correct the university, Sensa University, I'm not quite sure. They edited human embryos that the offsprings are now resistant to HIV virus. And actually 2 twin baby girls were born last month. And this experiment gained like a global outcry, and it was globally condemned because we cannot design humans. And someone could easily say that the idea is something beneficial and something helpful. We will have people that they won't get affected by viruses anymore. But is it just, CRISPR is a technology that it's still known, but it's quite recent. And of course, it works in a lot of organisms, but the human genome is complex. When we don't really know the exact origin of some disorders, some infections with viruses, or how genes are connected with therapy, how we can implement this technology without thinking of the risk that it may happen. Going back to good news and not bad applications anymore, we have a lot of CRISPR applications related to therapeutics. And Editas Medicine is the first company that managed to get FDA acceptance in clinical trials for treating patients with the rare genetic eye disorder that leads to childhood blindness. And it's important to say that for this disorder, there is no actual treatment these days. And it's the first time, and after years of studying for this company, that they decided, that FDA decided it's worth trying, it's a treatment worth looking for. And going back to my major, the food industry, and what I would like to see in the future, and applications like what I did in my yeast strains, a simple gene deletions. And also what the Swedish researcher did with creating a cabbage with just deleting a gene. Those deletions and those examples are something that it can even happen naturally during evolution. Deletion of genes or alteration of genes is something that can happen in nature or is even happening today with traditional breeding techniques in agriculture industry and also in brewing industry when you create new hybrids. So CRISPR is just doing this alteration more precisely and quicker than it used to be in the past. So why we should label this technology under the GMO legislation, as it's just a new breeding technique, and it can and researchers can have it completely under control. It's important to say that we have examples of mushrooms and other products, agricultural products, that they have been accepted from the USDA for for consumption and food utilization, and we have the first mushrooms, the CRISPR mushrooms, that there is an enzyme deleted that is affecting the browning of the mushroom, and they are actually ready for consumption in USA. But in all those products that there are nutritional products and they are aimed for food consumption, it is important to include risk assessments and hazard analysis so scientists and the public will be 100% sure that there is no negative impact on the human health. I believe that in the next years we are going to see many more examples, many more studies in the food industry, in agriculture, in medicine and therapeutics with this technology. And I think it's something that the public should embrace and be open, but also don't forget to be skeptical.
Thank you, Konstantina. The Swedish researcher, he ate his own cabbage.
Yes.
CRISPR cabbage. Did you try with the beer? Did you drink the CRISPR beer?
We didn't drink the CRISPR beer because we didn't have the capacity to make it in a real fermentation tank. We did a lab scale experiment, but we have it in our plants to make a brew with those things. And I think all my team in the university would drink it.
Everyone would drink it.
Yeah.
Great. And it's not the beer that we're having out here?
No.
Okay.
This is not a CRISPR beer.
Okay, great. Thank you very much.
Thank
Give
you.
Konstantina a hand.